Morning, everyone. I'm very happy to have Yuval Wigderson.
Anything goes.
Today, Yuval will speak today about color avoiding paths.
Tomorrow about path avoiding colors.
Tomorrow about DC dimensions. And also on Thursday about the Hadwiger conjecture.
Odd Hadwiger conjecture.
Odd Hadwiger conjecture at the Princeton. Right? Okay.
Great. Thank you, Rédei. Thank you, everyone, for coming. So yeah, I want to tell you some stuff about this topic, but there's very little that I feel I must get to. So if you have any questions at any time, then please don't hesitate to interrupt. So eventually I'll get to color avoiding paths, but I want to start with just a few warm-ups. So these are some theorems I really like. So I'll start with, I think, 3 theorems that I think are great and that have really beautiful proofs. So the first one is, I believe it's the first theorem ever proven about tournaments. So I think Rédei in the 30s was the first person to talk about tournaments. And what he proved is that every tournament has a Hamiltonian path. So just to remind you, a tournament is a complete directed graph. So I have n vertices, and for every pair, I pick one of the 2 possible directions. Hamiltonian directed path, I guess. So you have a path following the directions of the arrows in the tournament. It goes through all the vertices. And in fact, there's a bunch of different proofs of this theorem. Rédei actually proved a stronger statement that every tournament has an odd number of Hamilton-directed paths. So if you want a difficult exercise, you can try to think about how you would prove that. But there's a bunch of proofs of this simpler statement. Since this is a computer science seminar, I will show you an algorithmic proof. This proof is basically due to and the proof is super simple. So what you do is you draw the vertices of your tournament, and you arbitrarily label them V1 up to Vn. And you check if just along this ordering, every edge goes forward. Okay, if all the edges go forward, then you definitely have a Hamiltonian path. So maybe some edge goes backwards, like this one. What you'll do in this case is you'll just swap these 2 vertices. So you'll just change the order by swapping these 2 vertices, and then you keep going. So just at every step, you check if you have a Hamiltonian path along the bottom, and if not, you swap 2 vertices that witness this. Okay, so obviously, if this process ever terminates, then you're done, because the only rule for terminating is when you find a Hamiltonian path. So all you need to show is that it does terminate, and so you need to find some invariant that only increases. And the good invariant to use here is, you'll notice that the number of forward edges always increases. So I'm always going to track just among all the edges. So there are other edges as well, like this one. So maybe some of them go forward, some go backwards. But every time I do one of these swaps, the number of forward edges will strictly increase. It'll go up by exactly 1, because the one edge that I swapped certainly used to go backwards, now it goes forwards. And every other edge, its orientation is the same as it was before. So I have some invariant that's finite. I mean, it's not invariant, a monovariant. So it starts at something, it's capped at most entries do, so this process must terminate at some point. So if you think this is basically bubble sort in some sense, except on a term. Okay, so that's basically a proof.
Can you do other sorts?
Yeah, so actually there's another nice proof of this that I think of as insertion sort. So you can always grow, you can start with a path of like 1 or 2, like an edge. You can always grow the path by basically doing some sort of insertion sort. So yeah, so you can think how this would work. Yeah. And I mean, so this gives you also an efficient algorithm for finding this directed path if you want to find it. Other proofs I think don't give algorithms, but both of these are algorithmic. Any other questions?
Well, I mean, why does it have to do with the bubble sort? I mean, it's not a sorting
So
question,
it's not sorting. I mean, I'm sort of joking.
but then you said also.
Yeah, I mean, okay, so the reason it's kind of like bubble sort is that you're always comparing consecutive ones and doing the swap, and you're sort of tracking, the reason this terminates is sort of you are making some sort of progress. So in this sense, it's something like bubble sort.
No, but if this tournament really describes linear ordering, then this is public.
Exactly. So if this is a transitive tournament and you started with some sorting of it, some ordering, then this will literally just be the bubble sort algorithm. And that's transitive is the only tournament with a unique Hamiltonian path. And sort of this is the Hamiltonian path. The unique one is precisely
You need
describing.
to find that one.
You need to find the correct order. Yeah. So it's okay. Yeah. I mean, it's not the world's deepest analogy, but yeah. Good. Other questions? So that's warm up theorem 1. Theorem 2 seems completely unrelated, except that it was also proven by some Hungarians in the mid-30s. And it says the following. So every sequence of n real numbers has a monotone subsequence length at least square root n. So yeah, so when we walked into this room, some 4 of us came in sorted by height, right? Because we walked in some order and some subsequence of length 4, because I quickly estimated how many people there are here. It's between 4 squared and 5 squared, so yeah. Anyway, okay, so probably many people know this theorem. I think it seems totally unrelated to that thing. So let me try to make it seem a little bit more related. This is basically equivalent. So the basically equivalent theorem says that in any red, blue coloring of the edges of, let me say, of the edges of an ordered Kn. So you have a complete graph on n vertices, and you think of it as ordered. So the vertices are labeled 1 up to n, and you really care about their ordering. Then you color the edges red and blue. So in any such coloring, there exists a monotone, monochromatic path of length at least root n. And throughout the rest of this talk, whenever I say length of a path, this will always be number of vertices. Doesn't really matter, but just to be 100% consistent, I'll always mean number of vertices. Okay, so the statement is you have nothing about real numbers anymore. You just have a complete graph whose vertices are ordered. You color the edges red and blue. No matter how you do this, you're going to be able to find a monochromatic path, so all the edges of the same color, that's monotone. So the vertices come in the right order with respect to the ordering, whose length is at least root n. And it's easy to see that this implies this. So what you'll do is if you have your sequence of real numbers, just make them the vertices of your tournament and color an edge red if the left endpoint is less than the right endpoint and blue otherwise. And then this monotone monochromatic path is precisely the same thing as a monotone subsequence. So yeah, this one is actually sort of strictly stronger, but they're almost the same thing. Any questions about the statement? Okay. This one, yeah, the original proof of Erdős and Sekres was not very hard, but the really sort of best proof of this is due to Seidenberg from the 60s. And Seidenberg says to do the following thing. Label each vertex by a pair whose indices, whose coordinates are length of longest blue, really didn't plan out where to write this. Length of longest blue path ending at, so let's say you label every vertex V by a pair, which is the length of the longest blue path ending at V, and the same thing but in red. And by path, I again mean monotone, monochromatic. So just for every vertex, you write down what's the longest blue monotone path ending at that vertex, comma, what's the longest red monotone path.
And ending means the vertex is the largest.
Yes, exactly. So it's monotone, so it's going from left to right, and ending means that this is, like, that's the last vertex of the path, exactly.
But it can't be the smallest.
Sorry, yes, ending, yeah. I guess not like an endpoint, like the last one. Yeah, exactly, yeah. Yes, very good question. And now the almost trivial observation is that different vertices must have different labels. And the reason is, think of any two vertices, and let's imagine that they were joined with a red edge. Then any red path that ends at this vertex, I can definitely extend it by at least one to get to this vertex. So the length of the longest red thing ending here must be strictly larger than the length of the longest red thing ending here. It might be more than one more, but it's certainly at least one more. And of course, if this edge were blue, I would say the same argument with blue. So definitely when I record both of these numbers, all vertices have distinct labels. But I have n vertices, so I need to use at least n labels. So the entries in these labels, somewhere I must see something at least root n, because otherwise I'd have strictly fewer than n. But that means that somewhere I have definitely a path of length at least root n. So I know. Okay. Questions?
Is this tight?
Yes, it is tight. So it is tight. We'll see a more general version of this later, but the example showing that it's tight is the following. Split your universe into root n blobs of size exactly root n. So it's tight when n is a perfect square. Put, let's say, red inside all of them and blue everywhere else. And so what you see, certainly the longest red path is the length root n because it has to be inside a block, but you have any blue path must traverse distinct blocks. So there's root n as well. Yep. So it's exactly tight. Good. Any other questions?
No, only talking about tournaments.
So here there's sort of no tournament at the moment. So here it's a graph. So I don't have directions, but I am thinking of it as ordered. And indeed, this will come up later. So an ordered Kn is really the same thing as a transitive tournament. So as I've stated this theorem, it's about ordered complete graphs where the edges are undirected, but the vertices have an order. But that's really the same thing as a transitive tournament. So a transitive tournament is one, which is exactly this. I have an ordering and all the edges go forward. And then indeed, the way these two things are sort of more related is that under this, a monotone path is in correspondence with a directed path. Because in a transitive tournament, the only directed paths are the ones that are monotone with respect to the ordering, and vice versa. So, I mean, this only makes, the second thing only makes sense within transitive tournaments, but yeah. So an equivalent way of saying this theorem is indeed that now I color the edges of a transitive tournament in red and blue, and again, I want to find a directed monochromatic path of like at least root n, and that's precisely the same as this theorem. Yeah.
You said this was the best proof. Is there some database that contains the best proofs of all these theorems?
So this one is in proof from the book, in the book called Proof from the Book.
Yeah.
This one I think is not, but
It should be.
it should be. Yeah. And well, in a second, I'm going to show you another proof. So like I said, starting out with some favorite theorems and some really nice proofs. I'm going to do one more, which I think should also be in the same database. But Yeah, so now everyone, you'll read this all over the place, and everyone agrees this is like the right proof of this theorem. Any other questions? Okay, so last warm up. So the theorem that was proved independently in the 60s by Galay, Hasse, Roy, and Butaver. So now all four of these people found this and didn't know about one another. So yeah, I don't know. I mean, he was in Russia, he was in France, she was in Germany, and he was in Hungary. So somehow they didn't really communicate with one another or something. But it says the following thing. It says, every orientation of a graph G. So by orientation, I just mean edge orientation. So for every edge, I choose one of the two directions. So I have some graph G. No matter how I orient its edges, every orientation has a directed path of length at least the chromatic number of G. So you have any graph and any orientation of it, you'll be able to find a directed path whose length is at least the chromatic number. And this bound is best possible because if you have your graph, you can split it into chi of G independent sets and just direct all edges forward between the independent sets. And so that would be the longest. Okay, everyone okay with the statement? So let me show you the proof. It's going to be the same as that proof. So I'm just going to say, label each vertex by the length of the longest directed path, say vertex V. You just label each vertex by the length of the longest directed path ending in V. And now what's the observation? If you have any two vertices, U and V, and let's say they're joined by an edge in this direction, it's the same thing, right? Any directed path which ends at U, I can extend by 1 to end at V. So what I find is that adjacent vertices receive distinct labels. So if adjacent vertices are receiving distinct labels, I have a proper coloring of the graph, and therefore the number of colors I use must be at least the chromatic number, so therefore there must be a vertex labeled by at least chi of G, and I'm done. Make sense, everyone? Okay, it shouldn't, because this is a super wrong proof, the thing I just said. So this is not true. Here's the reason it's not true. This picture that I persuaded you with doesn't work. So here's an example showing you why this can't possibly be true. Imagine that my graph was a cycle and I direct it cyclically. Then every vertex is the endpoint of the path of length n. So it's definitely not a proper coloring. I actually have just one color. So what was the mistake in this proof? I drew it like this. But it's possible that the longest directed path ending at U already visited the vertex V, and then I can't do this extension. So, I mean, if it looks like this, I'm happy. But if this path actually already visited this vertex, then this is nonsense, and that's actually exactly what happens in this picture. Okay, so this proof is wrong. Everyone okay? Okay, but it's sort of almost right. So here's the way of fixing it. This is a really cool trick. What we will do, okay, so maybe ignore this part because it's wrong. What we'll do is we're going to let H be a maximal acyclic subgraph. So I'm just going to keep adding edges of G to H while maintaining it being acyclic, so not having any directed cycles, and I stop when I can't. So every additional edge of G, if I were to add it to H, I would close a directed cycle. So I can always find one of these. And then I do the same thing. So then I label vertices by the length of the longest directed path in H, ending at V. So I pass to the subgraph, and then I label vertices by the length of the longest directed path in H that ends at that vertex. And the claim is that even though I've only used H, this thing is still a proper coloring of G itself. So the claim is that this is a proper coloring of G. So if I can prove the claim, then I'm done, right? Because then again, I will have I need to use at least chi of G many colors, so I will have some vertex, that's the endpoint of a directed path, even in H of length at least chi of G. Is everyone okay with what I want to
So H, it contains all the vertices.
All the vertices, exactly. It contains all the vertices, and I keep adding edges as long as I can while not creating directed cycles. Exactly. Okay. So I need to show that this is a proper coloring of G. So I have, again, two vertices, U and V. And let's say they're joined by an edge. They're adjacent in G. And we might as well assume it's oriented from U to V. Doesn't matter. Okay, if this edge is in H, then they definitely receive distinct labels. Because then this nonsense argument actually works, right? If these guys are joined by an edge in H, so if this edge is in H, then it really is the case that the longest directed path ending at U has not visited V yet. Because if it had visited V, that would be a directed cycle. So then I really can do this thing of extending by one, and I'm done. So if it's an H, I definitely am happy. They have distinct labels. What if it's not an H? Same picture. Now I have this edge, but it's not. It's an edge of G, but not an edge of H. So by definition, what it means to be an edge of G, but not to be an edge of H, is that were I to add it to H, I would get a directed cycle. So there has to be entirely in H, this directed path like this, which is entirely in H. But we just argued that along edges of H, these labels strictly increase. So this label is strictly less than that one, which is strictly less than that one, which is strictly less than that one, all the way along. So the label of this must be strictly less than the label of this. And in particular, they're not equal. So again, adjacent vertices get distinct labels, and the rest of the proof goes through. Okay. Any questions? Yeah.
So like the four people get the same proof?
I think so. Yeah, more or less. I've looked at maybe one or two of these papers, and yeah, I think they're all roughly along these lines, but this is somehow the sort of slickest way of saying it. Yeah.
And the largest path in H is the same as the largest path in G?
Not necessarily the same, but it's like at least you will always get a path of length the chromatic number in H. It could be that there's an even longer path in G. Yeah. Okay. Almost done warming up. So let me just say, sorry, any other questions? I'm happy. Okay, so the corollary, this is sort of the thing I wanted to drive at. So this was observed independently by Flatel and by Dreyfus and Lehel. It says the following. In any Q coloring of an n vertex tournament. Sorry, I mean Q edge coloring. So you have an n vertex tournament, an arbitrary one. You assign its edges one of Q colors. No matter how you do this, there exists a directed monochromatic path with length at least n to the 1 over Q. So every tournament, no matter how you Q color its edges, you'll have a directed monochromatic path of length at least n to the 1 over Q.
All the tournament.
No, a tournament.
The vertices.
No, the vertices are not ordered.
What
It's
is the-
a directed path in the tournament. Yeah. So it's, I mean, you're, I think, correctly noticing that this is somehow related to this one, and that's why I was doing this thing that ordered is really the same as transitive. But this is even more general because it's an arbitrary tournament, not just transitive. Okay, everyone okay with the statement? So the proof is one line. It's some color class has chromatic number at least n to the 1 over q. So this is a just general property of chromatic number that whenever I decompose a graph into the union of, let's say, two subgraphs, the chromatic number of the big guy is at least the product, sorry, is at most the product of the chromatic numbers of the small ones. So here,
The edge coloring,
yes,
what constraints does it set?
Nothing.
Nothing.
arbitrary coloring with Q colors, arbitrary tournament, no constraints whatsoever, yes? But the general property is that, I mean, the way of saying it, it really doesn't want to go up more, okay? So the observation I'm using here is that for all the graphs G1 and G2 on the same vertex set, the chromatic number of their union is at most the product of their chromatic numbers.
Because you assign them just a pair of colors.
Exactly. So you can get a proper coloring of the union by just coloring it by its color in the first graph, comma, its color in the second
Are
graph.
you talking about vertex colorings now? Or?
Yes, sorry, very good. Yes, by chromatic number, I always mean the, yes. Sorry, yeah, absolutely. Yeah, so here I'm talking about the chromatic number, so vertex coloring, yeah. So just, this is a general property about unions of graphs, that the chromatic number is submultiplicative. So a consequence is that if I split Kn, which has chromatic number n, into the union of q different graphs, one of those graphs must have chromatic number at least n to the 1 over q. So some color class in this edge coloring has chromatic number at least n to the 1 over q. It has also some orientation coming from the tournament, but I can apply the Galilei-Hasse-Rho-Vital theorem to say that in that color, I can find a path of length at least the chromatic number, which is precisely this n to the 1 over q. Yeah.
Do you have a fast algorithm for finding such a more common?
I don't know how to. Yeah. I think I believe this is NP hard, but I'm not 100% sure.
If it always exists, then it cannot be NP hard.
Okay, fair enough. Yes. Yeah. Okay, but yeah, I don't know. Yeah. Yeah, I don't know if someone knows.
No, it's more like, it's related to chi of G, right? And so for example, given a graph computing length of this in every orientation, that could still be NP.
Couldn't you just run this algorithm in each color class? And then find.
Oh, yeah, probably.
Along this path.
Yes,
Like, you
probably.
don't need to compute the.
That's right. You don't need to compute the chromatic number. You just need to find a path of length at least this. So I think Maya is right that this proof of this theorem is algorithmic. And so then just do it in each color class, and this should probably work. Yeah. Other questions? So, I mean, somehow this theorem is what I've been building up to this whole time, because this actually subsumes all of the previous ones. And the previous ones are like very, very special cases of this one. So this theorem up here is just the one color case of this theorem down here, right? It says I have any tournament, I assign its edges one of one color, and I have a monochromatic, doesn't mean anything, directed path of length at least n to the 1. That's precisely a Hamiltonian path. So, I mean, it's kind of rare to see like Ramsey theoretic statements that are interesting already in the one color case, but this one really is. It also implies this theorem, again in a very special case. This is the case of two colors and just transitive tournaments. So transitive are a very special class of tournaments, but already this theorem is quite interesting. And it's precisely this when applied to a transitive tournament and two colors. And actually for the same reason, we can see that this bound of n to the 1 over q is tight, because maybe I'll try to draw it down here, but you can do the same construction. So this is tight already for transitive even, because what you can do is split into n to the 1 over q pieces and put the first color across. Then inside split again into n to the 1 over q pieces. And put the second color inside. Sorry, across. And then recurse q levels down. And you'll see that again, if it's transitive, so we think of it as ordered like this, the longest monochromatic path is of length exactly n to the 1 over q, because let's say in this top level color, you need to hit each thing exactly at most once. In the second color, the thing is disconnected. So you have to live inside one part, and within that top level part, you need to use each thing at most once. So it's, yeah. So it's down this tight. Okay, very good. Any questions? Okay, so believe it or not, that was just a warm up. So let's get to the actual meat. So the topic of today is color avoiding paths. And so here is the question that I want to ask. So definition, denoted G sub Q of n. So I'm sorry, this is like many combinatorics talks or papers that say, we define this function with these 7 parameters to be this minimum of this maximum of whatever. So I'm just going to write it and then explain what it means. So this is the minimum over all Q edge colored and vertex tournaments of the length of the longest color avoiding directed path. And so color avoiding, means exactly what I hope you think it means, is I have Q colors total, maybe red, blue, and green. I want to find a path whose edges see at most Q minus 1 out of the Q possible colors. So there's one color that they miss. So this means there's at least one color we don't see. Okay, so the function we're interested in is, so the theorems we're trying to prove are of the form, take any tournament, color its edges in 11 colors. What is the longest path you can guarantee whose edges see at most 10 colors? We want to understand how this quantity behaves. Okay, as a function of 11 and the number of vertices. So I think one obvious question is, who cares? That's kind of a random thing, right? So I actually want to spend a bit of time telling you why you at least could care. Don't know if you should care, but you definitely could. So one reason is that just very generally in Ramsey theory, so the most sort of classical Ramsey theoretic statements are kind of like this one or this one. You have some colored object, you can guarantee a monochromatic subobject that's kind of big, and you want to know how big you can get it. But actually these color avoiding questions are actually also a rather important area of Ramsey theory, where it's the same kind of thing. You have a Q colored object, you want to find a subobject as large as possible that avoids one of the Q colors. So one reason this might be natural is that in the 2-color case, these things are actually exactly the same, right? Because seeing only one color is the same as avoiding the other color. And so both are natural generalizations to more colors. But in many settings, actually, this color avoiding thing is somehow the better generalization. So like, if you care about the Erdős-Heinel conjecture, the multicolor version of it is really fundamentally about color avoiding and not monochromatic. And there's other examples like this. So that's one reason you might care. But the other reason is somehow this is a thing that shows up really naturally in a lot of different areas of math. So I want to tell you a little bit about some of these. Any questions? Okay,
What's conjecture you mentioned?
It's the Erdős-Heinel conjecture. It's about, so the multicolor version is, okay, the 2-color version, I have a graph, I forbid some induced subgraph, and I want to see how large of a clique or independent set I can guarantee. The conjecture is you can always get polynomial. In more colors, the statement is you have some 10 coloring of the edges of a complete graph, you forbid some fixed color pattern, and you want to find as large of a color avoiding thing as you can hope for, as you can find. And there, actually, if you think about it, monochromatic just isn't the right question to ask. Think about why, or I can tell you. Yeah. Any other questions? Okay, so one place where this came up in the 60s is Stein in the 1960s. He started asking about tripod packing. So what's this about? So I've prepared visual aids with the help of my 6-year-old niece. So this is a tripod. So a tripod, I hope you can all see, it's a bunch of 1x1 cubes that are glued together like this. So, so I take, let's say, length n, I have these 3 legs that are glued together like this. And the question that Stein was interested in is how efficiently can these things pack 3-dimensional space? So it's like some sort of sphere packing question, except this is your sphere. Okay, so you can ask, why? So Stein originally had some motivation from group theory that I don't understand, so don't ask me about it. Later, I think Goulomb came up sort of with the same question based on some motivation from coding theory. So this thing is sort of like a Euclidean version of a Hamming ball of radius 1, because it's like I have this sort of center, and I can change each of the 3 coordinates to anything, but sort of anything only in the positive direction. But it's some sort of Euclidean Hamming ball-like thing. So the question of how densely these things can pack is like some sort of Euclidean version of a packing, like an error correcting code question. Again, sorry?
Are they infinite?
Yeah, so for the original question, you can think of them as being infinite, and the question is how densely can you pack? But this is, by some sort of standard limiting arguments, this is kind of the same as understanding how many of these can we pack in a K by K box. So, and you want to understand the asymptotic K of this. So you want to put these center things, you want to put them at integer coordinates. So the center thing lives, this bottom corner has some integer coordinates between 1 and K. And the question is, how many of those can you fit without them overlapping? And for this question, you might as well assume that their length is just K, because infinity doesn't matter. Okay, this is a question you can ask. I won't get too much into what exactly is going on, but this can be converted into one of these questions. I'll tell you about how that works. So if you think about these things geometrically, there's kind of 2 ways 2 of them can interact when they're not overlapping. So the most simple one is this, which I'm going to call nestling, where this one just sort of lives entirely within the convex hull, like within the convex hull of the other one. The other thing that can happen is like this, which I'm going to call stabbing. So that's when the leg of this guy goes through the plane defined by 2 of the legs of this guy. So it's like stabbing the plane of the other one. Okay? And there's also a degenerate case, which is when the sort of bases are coplanar, when it sort of looks like this. And this I'm also going to call stabbing. So stabbing is when it intersects the plane of the other 2. Okay. So what you can do is you can form a 3-colored tournament whose vertices are your tripods. So given n tripods packed in this box, K cubed, we form a tournament. As follows. So if T stabs T prime, we direct the edge as T prime directed to T. So if this is the situation, the higher one is directed towards the lower one. And moreover, I need to color the edges. I'm going to color the edges with one of 3 colors. I'm just going to color it by the name of the direction that's doing the stabbing. So in this case, I'd color this edge Z. If it was like this, I'd color the edge X, because it's like the X coordinate is the one doing the stabbing. So, yeah, so I color by stabbing direction. And maybe I'll do it on this board because I don't want to crouch. On the other hand, if T nestles T prime, we direct from T prime to T and color arbitrarily. Okay, so whatever. This is a way of constructing a tournament and assigning one of three colors to every edge. Now, the reason this has to do with anything is if you think about a color avoiding path in this tournament. So here's the fact that you should think about geometrically. So any.
So can you just draw what you just wanted?
Yes.
Nestles, I mean, which one nestles which one?
Sorry, yes. The outer one nestles the inner one, like the outer one is hugging the inner one, and you direct it from the inner one to the outer one. And I'll explain why in a second. So it'll follow directly from the claim I'm about to write. So any directed path avoiding color, let's say Z, avoiding the Z direction. So let's say on any directed path avoiding color Z, the Z coordinates. Wait, did I say this right? No, I said this backwards. I'm sorry, go on. I think we want to go up, yeah. On any directed path avoiding color Z, the Z coordinates of the apex, the like base point, strictly increase. So if I avoid color Z, then the Z coordinates as I walk along the path are strictly increasing. And the reason is, what would it look like if the Z coordinate ever went down? The only way it can go down is if it looks like this. Like that's the only way that this guy can be lower than this guy along a directed path. But then this guy will stab this guy in direction Z, so this edge would have received color Z. So if the path does not use color Z, the Z coordinates must be strictly increasing. Okay, so yeah, you have to think about how this works geometrically, but. So as a consequence, somehow these color avoiding directed paths sort of show up naturally in this question. And concretely, what you find is that if I can and tripods in this K by K by K box, then G3 of N is at most K. Because I will have constructed a tournament on N vertices whose longest color avoiding directed path has length certainly at most K, because my coordinates need to be strictly increasing along a directed path, and there's only K of them. Or said differently, lower bounds for this quantity give you upper bounds on this packing question, which is sort of what Stein was interested in. Okay, good. Any questions about that?
I got a bit confused. What's the dimension of the tripod?
So we're packing them in a K by K by K box.
Okay.
So the length you can think of as K or as infinity. It doesn't really matter.
So each of the legs just like.
Yeah, each of the legs.
Out of the bounding box.
Exactly. Like once you put the center at some point, you're not allowed to use anything in each of the three directions inside the box anymore.
But it's okay for them to like extend out of the box.
Yeah, they're allowed to extend out of the box. Yes, very good. Sorry, yes, absolutely. Yes. Sorry, I didn't say that, yeah. And it's because we really care about the sort of infinite tiling problem of how densely they pack space, but then by some sort of limiting argument, you'll look at a large box, see how much volume you can take up of that, take some sort of limit. Yeah.
So 3 dimension is the easiest case, or it's not?
3 dimensions is somehow actually, it's somehow the hardest case. Yes. Yeah.
Is it a 2-dimensional version of the question?
Not really, because the 2-dimension thing's just fully tile space. So the tiling density is 1. So, I mean, there is, but the answer is not very interesting. Yeah. Good. Any other questions? Okay. Maybe I'll do the other sort of motivations a little bit faster. So that was one motivation for this kind of question. Another one is due to Brass from the early 2000s, I think. He was interested in convex extremal questions. So the kind of question he was asking is you put a bunch of points in convex position, let's say on a circle, and you want to select as many triangles out of them as possible. You want to take as many triangles as you can while avoiding a certain classes of geometric configurations. So whatever, you can ask a million types of different questions. So you can ask, for example, I want to avoid any two that look like this, or the one that turns out to be really important is avoiding any two that look like that. Right, but like you can just ask what are the different ways triangles can interact with each other. You can say I want to avoid some subset of these configurations. What kinds, like how many triangles can I select as a function of the number of points? Some sort of natural extremal hypergraph question where the hypergraph is constrained in a geometric way. Okay, and so yeah, there's like 10,000 different questions of this type you can ask because you can rule out any sort of kinds of configuration. Almost all of them are really easy. So they just don't, they're all really quite easy. It turns out that a really hard one that Brass had no idea how to answer was avoiding this configuration as well as two triangles sharing an edge, sharing 2 points. So you avoid this and you also, let's say, avoid this one. So it turns out that if you try to forbid these 3 things, it's really hard. Brass had no idea how to do it. And it was noted by Aronov, Dujmovic, Morin, Ooms, and Schultz Javier de Silveira that this question is also one of these questions. So you can convert this kind of thing into a 3-colored tournament such that you don't have a particularly long directed path. And so again, lower bounds on this quantity correspond to upper bounds on this geometric question. In fact, it turns out to be basically equivalent to this tripod packing question. And it's another one of these. It's not, the connection is not very hard, but I'm going to skip it because I'm watching the clock.
For which cube?
3 again. Yeah. So somehow this question was mostly studied in the 3-color case. Some of these motivations arise mostly in the 3-color case. Okay, and so there's another couple of connections that maybe I won't tell you too much about. So Potion Low came up with this question exactly. He was studying something called K-majority tournaments, which are a natural class of tournaments people care about. There's certain questions that people are really interested in. He had a construction that he didn't know how to analyze, but he noticed that analyzing the construction basically boils down to solving this question. So that's how we came up with this question. And then also, we recently discovered, or Cosmin Peralta told us that there was a math overflow question about correlated sequences of correlated random variables with a certain property. And then Will Sawin and Terry Tao answered it using some crazy Fourier analysis stuff. And that exactly corresponds to this question when you restrict to transitive tournaments. And so somehow this question, using Fourier analysis, you can answer it for transitive tournaments, more or less exactly. but somehow that connection doesn't work for non-transitive tournaments. But yeah, some weird, you go to probability and then some Fourier analysis on it, but it's really the same as this combinatorial question. Okay, so that's some background. So let me tell you what we know about this question. Any questions first of all?
For the triplex problem, does the tight example lead to an example to the triplex problem?
No. Yes. So, yes. Yeah. We have no idea what the answer to the tripod question is. And yeah. Yeah. So that leads me very well to what we know about this question. So again, we're interested in this function. We're Q coloring the edges of a tournament, arbitrary tournament, and we want to find as long of a directed path as possible. We want sort of the worst case. So we want to minimize over tournaments and over colorings. So the first thing that perhaps Maya observed is that this is certainly in most n to the 1 minus 1 over q. And so what is an upper bound on this? It's an example. And the example is that example. So take a transitive tournament, color it like this. The longest color avoiding path you can find is of length n to the 1 minus 1 over q. Because, I mean, right, like if you're avoiding, let's say the red color, you're just entirely within one of these blobs. If you're avoiding the blue color, you can only use sort of one of these blobs, then hop with red to this thing, use one of these. It's again going to be n to the 1 minus 1 over q. That's the upper bound. For a long time, as far as I know, the only lower bound people knew was root n, which was in particular independent of q. And this is really stupid. So what you'll do to get this lower bound is just arbitrarily group your colors into two buckets, apply the Erdős-Thecker's result that in these sort of new supercolors, you have a monochromatic path of like root n. Since it's monochromatic, it only uses either this bucket of colors or this bucket. So certainly it avoids all the colors in the other bucket. And this was the only known lower bound. There were tiny improvements on the upper bound, specifically in the case of three colors, which I was saying is sort of the most studied case in the past. So this was first due to Hamacher and Stein. So Hamacher and Stein showed that in three colors, they had a construction that does n to the 0.663, which is less than 2/3, which is what this is. So this is better. And they actually did this by constructing something for this tripod question. They had a construction for the tripod thing, some nice recursive thing, and you get some exponent, which is better than 2/3. And very interestingly, this is the tournament here is highly non-transitive. So somehow this example that was kind of tight for the monochromatic question, was exactly tight for the monochromatic question, is transitive. But at least here, you can do better by doing something highly non-transitive. It is conjectured by a bunch of people that n to the 2/3 is the truth when restricted to transitive. Somehow doing better than 2/3 should really be a non-transitive kind of feature. Then there were a bunch of improvements. The record is due to Gowers and Long, who have another random exponent, which I will write down for you. N to the 0.647. So this is Gowers and Long. They had a really cool sort of way of getting a continuous relaxation of this question and then doing some continuous optimization. And so this is the optimum of some random function. Actually, there is somewhat good reason to expect that this might just be the truth in the three color case. So like this random number is maybe the truth. I don't know how strongly I believe it, but some people believe it. Okay, and the only lower bound was just root n always. No one knew anything better than root n. And Gowers and Long sort of explicitly asked to narrow this gap, right? As q gets larger, this gets worse and worse because the upper bound is tending to 1 and the lower bound is stuck at root n. And so the theorem that we proved, which I optimistically thought I would tell you a little bit about the proof of, but probably not today. The theorem we proved is that the exponent tends to 1. as Q grows. So concretely, what we proved is that GQ of n is at least n to the 1 minus some constant over root log Q. The precise dependence here doesn't really matter, and it's just what we get from the proof. But the important thing is that as Q gets larger, this thing is tending to 1. So, I mean, it's kind of what you would expect, right? Because this lower bound here was really stupid. You were just throwing away the fact you have all these different colors. And so, in fact, you really should be getting, as the number of colors is growing, avoiding one of them should be becoming harder, should be easier and easier because you have more of them. So there's more that are easy to avoid, so you should be able to find longer and longer paths, and that's indeed exactly what this is. Okay, so that's the theorem. Any questions?
What's the proof?
I won't tell you, but I'll tell you one thing which is really cool. This is one of the key lemmas that I think I will be able to prove for you. So I told you, sorry, before I say answer these questions, anyone else have a different question?
Yeah. Do you get anything better than root n for the case of q equals 3?
No, so unfortunately, yeah, for q equals 3, we don't do anything better than root n. Our proof maybe starts doing better than trivial at like 200 or 300 colors. So, I mean, we didn't try to optimize this, but certainly less than 10, there's no hope. And I don't know, 20 maybe we could do with some optimization. Yeah.
Also, you think 1 over square root log q? Yeah.
No, there's no reason. I mean, it's basically we have proof is like you either win for some reason or you win for another reason, and this is what you get by balancing the two of them. But there's like, I don't see why these should be the only two reasons or why you shouldn't be able to, you know, if you're close to being tight here, you should be able to do better here or something. So no, there's no reason to think. I would guess that this is probably closer to the answer. I would say that 1 over q is more like the right behavior, I would think. Yeah. Any other questions? Okay, so the Q lemma says the following. So if T is delta far from transitive, so this means that you must reverse, sorry?
It's hard to see this on the video.
Okay. Let me try maybe yellow. So delta far from transitive means you must reverse at least delta n squared edges to be transitive. So your delta close to transitive, if you can be made transitive by flipping the orientation of at most a delta fraction of your edges, otherwise you're delta far from transitive. So I think people call this like a minimal feedback arc set. The minimal feedback arc set has size, please delta n squared. Anyway, lemma says if you're delta far from transitive and T is Q edge colored, then T contains a directed path of length omega delta squared n over q cubed, seeing at most 3 colors. So if you're delta far from transitive, so these random parameters don't matter so much. The important thing is that this is linear in n. If you're delta far from transitive, you have a linear length path which sees only 3 colors. So in particular, if your number of colors is at least 4, then you automatically have a linear length color avoiding path. So somehow this thing where these constructions are highly non-transitive, that's like fundamentally a 3-color thing. 3 colors is really different from more colors for this question, which is one of several reasons why our proof doesn't really say anything about the 3-color case. But yeah, the second, I mean, this statement is also true in the 3-color case, which is not interesting. But just if you're far from transitive, you can find a linear length path, which sees only 3 colors. In particular, is color avoiding if Q is at least 4. And so this is really nice because it means that in our proof, we can more or less focus on, I mean, we focus on the close to transitive case, And that's a lot easier to work with. Somehow things are a lot cleaner when you're close to transitive. And it really has to do with this kind of issue we were running into here. Certain arguments of this type work very nicely when you don't have directed cycles, but don't work when you do. And by being close to transitive, I mean, it's not like you have no directed cycles, but you can do stuff. Yeah.
So the mass overflow solution uses Fourier analysis
Yes.
representative ones. So are you also using?
No, so yeah, somehow that, as far as we can tell, that proof is very specific to the exactly transitive setting. And we, of course, need to tolerate, we're 1% far from or close to transitive. And we really need to be able to tolerate these errors. I mean, it's 1%, but it's 1% of all the edges. So you need to use them. But somehow we have this a completely combinatorial argument, and it's just sort of robust enough that you can clean up the noise arising from the edges that go the wrong direction. Whereas, yeah, the Fourier analytic thing seems to be completely in the exactly transitive setting.
Does the argument recover basically the same kind of bounds for the transitive?
No, in the transitive, their Fourier analytic thing does much better. It will get something that's inverse linear in Q. In fact, for large Q, they get basically the right exponent. So it's like 1 over 2Q, like that. Okay, so maybe in the last minute, I will just tell you how we prove this. So the proof is we use another lemma. So this is a fact due to lemma prime, due to just my co-authors from maybe 15 years ago. If T is delta far from transitive, it has omega of delta squared n cubed cyclic triangles. So there's a fact that you all know that a tournament is transitive if and only if it has 0 cyclic triangles. This is a useful fact to know. It's a robust version of that. So if you're delta far from transitive, you have a lot of cyclic triangles, and you even get a nice polynomial dependence on delta. So you can think of this as like the triangle removal lemma, but for tournaments. But somehow in the triangle removal lemma, we can't get polynomial bounds, but in tournaments we can. It's just quadratic. And this is, this is clever, but it's really just sort of elementary double counting and averaging. It's not rocket science, but it's, yeah. Okay, so we're allowed to assume we have a lot of cyclic triangles. So what this implies is that we have at least many cyclic triangles seeing the exact same colors just by pigeonhole. So we have many cyclic triangles. By pigeonhole, we can select a 1 over q cubed fraction of them that see the exact same triple of colors. And okay, then you do one of these annoying arguments where you keep throwing away edges that lie in much less than the average number of cyclic triangles of the specified color palette pattern. So now you can actually assume, so by a little bit of work, you get at least delta squared n over q cubed edges. Sorry, you get a collection of edges which each lie on omega of delta squared n over q cubed cyclic triangles of this color pattern. So this is just so you delete the ones that lie too few, you keep going and you count how much you delete. Okay, and now we're done. So the thing is that now take one of these edges. It lies on one of these triangles. Let's say it's red, green, blue, cyclically arranged like this. Now go to this edge. It also lies on many triangles with the same color pattern. So in particular, it lies on one that uses a vertex we haven't seen yet. So it lies also on a green, blue, red cyclic triangle going like this. Now look at this edge. It also lies on many of these, including one that we haven't used this vertex of. So that one lies on a blue, red, green cyclic triangle. And now go to this guy and keep going. And you see that at the bottom, we have a nice directed path that uses only the three colors that we've seen. So that is the proof of the key lemma, and I think I'll stop there. So thanks for listening.
Questions, comments?
Where does the root log come in?
Well, it's from the part of the proof that I didn't tell you anything about, but yeah, so we basically have two different ways of finding one of these long paths. So we split our tournament in half and we apply induction in each half. And either we can sort of glue together a long path here and a long path here in some very robust way, or we robustly can't. And then that means that actually in one half, we get some very good structure that we then just in one half, we find something much longer than just the naive actually tells us. And there's just a balancing of, I mean, you have to pick some parameters and you want to balance these two effects that give the same bound, and root log Q is what comes out of that.
That's two halves now, isn't it?
No vertices. So you just split your vertex set in half, you apply induction on the left, apply induction on the right.
It's not clear why log Q.
No, it's not clear why log Q, but yeah. I mean, it's because basically you want to do something, like the reason more colors is easier in some sense is you want to try to find a path avoiding red, try to find a path avoiding blue, try to find a path avoiding green. And you're okay if in one of these you sort of are really bad at doing it. So you want to do it sort of in some amortized way across all the different colors. And so that's why more colors is easier because you can amortize better. And that's the reason the error term depends on Q instead of N. But yeah, why it's log or root log, I don't think there's an easy way of seeing. And again, I don't think it means anything. I think it's just what the proof gives. Yeah.
So, how strongly are you using the fact that you started the tournament? Like, for example, would it work for more general directed graphs?
Yeah, so it would work as long as you have many edges, like close to and choose two edges. So in fact, as I was saying, using this, we can assume we're close to transitive. So in fact, we just sort according to this ordering, witnessing that you're close to transitive, and we'll just never use the backwards edges. So we could also tolerate that also 1% of the edges are just missing. I mean, we just say put them in as backwards edges, but we are certainly using the fact that we're quite close to n choose 2. So it wouldn't work with, let's say, just quadratically many edges, I think. Yeah.
Is there a version of the question that makes sense for sparser directed graphs?
I mean, you run into issues where your directed graph might just look like this, like complete bipartite, but all edges go forward. Then you don't have any directed paths at all. So you definitely need to be away from this. So that's why it has to be at least pretty dense. Yeah. I mean, so maybe there's some other things you can do, but I don't really see how to get a nice question.
So when you're applying this delta is truly some small fixed constant.
Yeah, delta depends on Q, but it's like 1 over Q to the 10th or something. Yeah.
But you could also apply this with delta being little o.
That's right. Yeah, we could apply it with delta being even some small power, negative power of n. It didn't end up being useful. We thought we might want to, but it turns out that it wasn't useful. So yeah.
Okay. Thank you.